Okay, why don't we start, guys? So, I don't know whether you just tune me out when I talk like this. I hope it makes sense. But I like to talk with you guys a lot about my goals as a teacher. I don't know if other teachers do this or not, but one of my goals is to help you guys figure out, do you want to keep doing physics? And I would say at this point, after even doing probably one test, you probably should have a good idea of whether or not your skill set matches what physics requirements are. I hope you have at least a rough idea, because I mentioned this earlier today. It doesn't get harder. All we're going to do now is just talk about more formulas. So if you understand problem solving, if you can do that, if you can figure out which formula to use, that's half the battle. If you understand how to mathematically rearrange stuff, that's kind of the other half of the battle. Does that make sense? There really isn't harder work to it, there's just more. Okay. So if there's something that you're struggling with, I mean, if you know that you have a weakness and you're not good at math, then let me know so I can help maybe try to target that weakness so you can get better. Or if you're just not great at problem solving, that one's a little harder to work at. But let me know, okay, so that I can try to help you work on things. While I'm talking about goals, like I said, I like to talk to you guys about some of my goals for classrooms. Try to explain why I teach the way I do, as opposed to just I teach you and you just have to go with it because I'm a teacher. So, like some of the other things that I try to do as a teacher, and I'll talk to you about, is I want you guys to do progress logs, because I think that it's to your advantage for you to be a part of the marking process, as opposed to it being me. Hopefully you'll agree. Like hopefully this helps you. Another one of my goals is, in a way, I want to help you guys figure out which courses to keep taking. I also want to make sure that I do a good job of giving you the foundational skills so that if you do want to go off and go to university one day and be in chemistry or physics, that you have exposure to that. That's one of the biggest reasons why I want to do labs in chemistry, because I don't want someone to graduate from FP Walsh, go to the university, and then they tell you, here, do some labs, and you're like, I don't know what a beaker is, because you've never done that before in your life. Does that make sense? And so, I mean, I guess maybe that helps explain. I do challenging things. Like I make you guys do labs, their conclusions, analysis, and results. But because it may not apply to all of you. Right? Like not all of you may eventually go off and become chemists. But I do it because for those of you who do want to, I want to make sure you have the skills you need so that you can do that if you want to. Does that make sense? So, okay, I'm getting off topic again. Let's talk about work. Okay. You guys have probably heard the term work at some point in your life before, get back to work. Physics has a concept of work, but the first thing I have to mention is that the everyday life idea of work and the physics idea of work, they are different. Okay? So like when I make you guys do quote unquote work, that's actually not the physics definition of work. So here is technically the definition of work in physics. It's the transfer of energy from something to something else. If there is an energy transfer, that means work happened. I skipped a word when I read that out loud. I skipped the word mechanical energy. Do you guys know what mechanical energy is? Yeah, it's a good way to describe. Can you say that louder? Yeah, like all of the energies kind of collectively is referred to as mechanical energy. So basically, if there's a transfer of some sort of energy from one type to another, that means work's been done. One of the best examples I can give you is this baseball and a bat. Okay. Someone throws a baseball, and I have a bat, and I try to hit it back the other way. You would have done work on the ball because the bat would have transferred some of its energy to the ball, and that causes the ball to go back the other way. Does that make sense? You have to be able to transfer some sort of energy somewhere. There's another definition we have of work. Work is done whenever a force is applied over a distance. That's another definition of work we have. If you were a baseball player hitting a ball, would it make sense that you're applying a force on the ball? Like there must be some sort of force happening as the ball gets hit. Does that make sense? And it actually occurs over a distance. It's actually a very small distance. Anybody watch the Blue Jays over the last couple of days?
Yeah.
One of the things I thought was really cool is watching, Jose Bautista's home runs are pretty cool, obviously.
Yeah.
But if you ever got a chance to see like the slow motion shot of like the bat and the ball happening like frame by frame, anyone seen some of those shots over the last little while? Okay. Sorry if you haven't, but hopefully this makes sense. You can actually like see the bat actually like warp just a little bit as it like wobbles, as Batista applies a force to that ball, making it shoot back the other way. And you can actually say that the ball and the bat were in contact with each other for a little bit of a distance. It's not a long distance, but like this ball and this bat are hitting each other over like, say, that amount of distance. Does that make sense? So long story short, work is done whenever you have a force and it also applies over a certain amount of space. That's what work is. So I also want to define the term force a little bit more specifically, because I'm sure you guys have heard that word before as well. You know, you probably intuitively know a force is like, I don't know, how strong something is. If you can use a lot of force, you're a strong person, right? Here's the definition of force. It's either called a push or a pull. So, like for example, if I were to push that chair, that's a force. I applied a force on it. Or if I had like a tug of war rope and I pulled back on it, that could also be using a force. So it's either pushing or pulling something. There is a really important side note I need to mention though. The direction of force and movement must be parallel each other. I'm going to highlight this section right here. This is a really key concept. Let's say that I push on this chair right here with my feet again, and I push that way. So my force is that way. And let's say that the chair, for some reason, happens to go up. I know that makes no logical sense, right? But hypothetically, let's say there's a scenario where you push this way, but it actually goes this way instead. Our world doesn't usually work like that. You would not be doing any work. The direction of movement and the way you're pushing have to be the same. Let me give you an example. Let's say that you're in an elevator. And against the elevator, you push against the wall. Is the elevator moving? Well, technically it's moving up. But is it moving up because you're pushing?
No.
No. Does that make sense? Now, if you were a person who, for example, was at the top of the elevator shaft, and you were Superman, and you were grabbing the elevator cable and literally pulling it up like this, does that make sense? Then Superman is doing work because he is lifting up with a pull, and the elevator is also going up. Does that make sense? But if someone pushes this way, so I'm doing like outwards, and if the direction of motion goes up, that's actually not technically work. Okay. I also want to remind you guys about another term that we've talked about before. Work and energy are very closely related. Do you guys remember how on the very first day we talked about energy, and I actually mentioned that energy is an undefinable term in physics? Like, it sounds kind of weird, but like we really don't have a great definition for energy. Actually, I lied. I do this a lot. Sometimes I'll tell you guys partial truths, because at the time it just makes more sense to tell you something, and then later I'll kind of fill in the blanks. There actually is a very good definition for energy. Here's the definition. Energy is defined as the ability to do work. Okay? If you have energy, it means that you're able to accomplish something. You're able to move something. You can do a force over a distance. That's actually the best definition for energy we have. So, sorry that I lied to you. I'm trying not to think of it as a lie. Think of it as like since we weren't ready to talk about work, I didn't want to talk about work on day one. So, new definition. Energy is the ability to do work. So, here's a formula that I think is on your formula sheet. Did I put that one on there, or did I even skip that one? Not on the formula sheet? Wait, write it on there.
Okay.
Yeah, it is. It is.
Okay. I don't know.
Did you even have the formula sheet in front of you?
Yeah, right here.
Oh, you just didn't see it. Okay, so here's another
Oh,
formula.
it is right there.
You found it now. All right. So new formula. This one is very straightforward. If energy is really the ability to do some sort of work, then literally energy is work. Okay. But I gotta be more specific. The change in energy is work. Let me give an example here. Let's say that you as a person have some energy in your body. Clearly you have the ability to do stuff, right? And let's say that you push something. Did I use up all of my energy to do that?
No.
Okay, so that's why it has to be the triangle symbol for energy. It's the change in energy. I gave up a little bit of my energy. I didn't use all of it, but I used some of my energy. and that energy was converted to work. Work meaning that I actually pushed the chair. Okay. So this is a really easy formula. If I ever give you energy or if I ever give you work, they're equivalent to each other. And then here's the second formula I want to add. This formula is that work is equal to force times distance. Okay, brief aside before we start doing some examples, because I think most of the rest of the class is just some practice questions. Okay. I need to talk about units. Okay. Distance is measured in meters, typically. F for force is measured in capital N's. Does anybody have any idea what capital N's refers to?
Newton.
Well done. Good. You guys have heard this before?
Yeah.
Oh, awesome. Okay, good. Newton's. It's named after Sir Isaac Newton. Okay. Work has two different possible units, and I want you guys to be able to use either of them, but typically we're going to use J. Yeah, good. Joules. So you guys have heard this before. Yeah. The other possible unit, though, is called Nm, and we call that a Newton meter. A Newton meter is actually the same thing as a joule. So I'm just going to write that in words for you. This is known as a Newton meter, and that's basically the same thing as a joule, but we're going to use joules most of the time just because it's easier, I guess. So. Let's try an example. Or actually, no, I guess I have pictures first. Well, I'll skip the pictures. You guys can... We'll do some examples. We'll skip the pictures. You guys can read them on your own. So first example. You exert a force of 25 newtons on your textbook while lifting it up to a height of 1.4 meters. How much work did you do?
25 newtons.
Well, 25 newtons is the force that you used.
Dude, we don't know that.
See, this right here is a force. And this 1.4 meters, that is a distance. That make sense?
Yeah.
So the formula is that the work you do is equal to force times distance. The force that you used was 25 newtons. The distance that you moved the book was 1.4 meters. So we just multiply those numbers together. Can I talk about that in 1 second? So is everyone okay with 25 and 1.4 giving you 35?
Yeah.
Okay, so now Naomi's question. They are different units. So the way this technically would work is you'd write a Newton next to an M, but rather than writing Newton meters, the preferred method I want you guys to do is call it a joule. 35 joules. What do you need?
Can I borrow Caitlin for 2 seconds?
She's okay with it.
I'll be back in 2 minutes.
Oh, wait. Did that make sense to you guys? Close the door. Apparently that was really important. Alright, next example. That first one was pretty straightforward, hopefully. Let me stop me if I lost you on that one. You just times the two numbers together. Okay, here's maybe a more challenging question. Here I'm going to tell you how much work you did. I'm going to tell you the distance you did. Our goal now is to try to find out how much force you required. So we're still using that same formula of work equals force times distance. Except now when I plug in numbers, W is not the number that I'm solving for. We actually know how much work we did. We did 64.7 joules. We don't know F. We don't know how much force we used. But we do know distance. Distance was 5.73 meters. Everyone okay with that first little bit?
Yeah.
So, algebra skills time. How do you get F by itself?
Divide by itself.
Good, yeah, divide by that 5.73. Before I do that, though, I want to make one subtle change. See how that's a J right there and that's an M? That doesn't really go well together. So I want to make a change. I'd rather than call it a joule, at this point here, can I go back and call a joule that Newton meter again?
Yeah.
So that's like N, M. I'm just going to change the joule back, in this case, to Newton meter. The reason why I want to do that is because hopefully now you can visually see that this meter right here will cancel with that meter. That makes sense? So now just divide the two numbers. 64.7 divided by 5.73. I get 11.2914 blah, blah, blah. Last step, just make sure you get the right amount of precision for digits. So, 3 digits. So 1 and 1 got to stay. The 2 is in question. But because it's a 9 afterwards, the 2 will rise up to a 3. So it's 11.3 newtons of force. Straightforward? Like I said to start class, physics at a certain point, I don't want to say it's easy, because physics is not easy, but it's the same. It's like new formula. If you get how to use the formula, it's just math. So. Let's do another one here. You use 3.4 newtons of force to hold your textbook and carry it 18.3 meters down the hallway under your arm. How much work have you done? So you might be inclined to say, hey, we've done this before. Work equals force times distance, and the force... But by the way, do you guys know that when I put a dot between things, that means a multiply sign?
Yeah.
Okay. Sometimes I try to avoid using an x because people think x is another variable. So. Your force is 3.4 newtons, your distance is 18.3 meters, so you times those together. I got 62 when I was done. I guess that would be in joules. And that is dead wrong. Yeah. So, back to the first half of those Venn diagram circles. You guys are great at the math, I'm guessing, if you can do that. Another part of it is the interpretation. I'm just going to diagram this, so I'm just going to pretend that I have a textbook here. I am holding the textbook. I am holding the textbook up. And I'm walking in this way. Am I doing work? No. Because if I'm lifting it up, but I'm walking that way, am I going the same direction as both? No. In order for it to be work, I do work when I lift the textbook up, because my force pulling up matched the book going up. But as soon as I start walking this way with the book, unless I'm pushing the book outward or pulling the book inward, I'm not doing work. Does that make sense? So this is a trick question. You're not doing any work, technically, in a physics point of view. Yeah. No work. Well, I think on a written response question, I'm going to ask you guys to talk about what's happening, but really your force is going this way. Your distance is going this way, and they're not the same direction. Oh, that's really bad. Let's try that again. Not same direction. So this would be like you pushing against the elevator and say, I'm making the elevator move. You're not. Does that make sense? The force you're applying is pulling something up, but the direction you're going is forward. That's not work technically. So that goes back to that first idea of you also have to have good reasoning and problem solving skills to understand the scenario. In this scenario, it's not actually work. Let's try another example here. Let's say that you are pushing with all of your might to try to make a rock move. There's just a really big rock and you decided you want to push on it. And the rock doesn't move. But I mean, you are pushing. Boy, you are getting tired, you're sweating, but the rock doesn't move. How much work did you do? None.
That's not pushing.
Yeah, because the only way that we actually get credit for doing quote unquote work in physics is if something actually moves. So in a way, it's like a force of 85.6 newtons times a distance of 0 meters. You did, again, no work. So let me go back to the start of class when I kind of mentioned that the definition of work that you guys use in everyday life and the physics definitions are very different. If I tell you do a lot of work as you're sitting in your desk, are you actually doing a lot of work?
No.
No. I mean, I guess maybe your hand is because you're moving it a little bit of a distance, but you're not actually doing a lot of work from the physics sense because there's not a lot of distance happening. You either get a lot of work because you go a long ways, distance-wise, or you do a lot of work because you're using a lot of strength and might. And I don't imagine too many of you when you're writing with your pencil are like really forcing down on your pencil all that much, right? So technically, when you're doing work in an everyday life scenario, you're actually not really probably doing work in a physics scenario. Okay, let's try another example here where I'm just going to throw some little twists in. Here's a championship weightlifter, and he's going to try to lift a barbell above his head. So like we're talking like one of those Summer Olympic like dead pull lifters. You guys know the thing I'm talking about? 180 centimeters. I'm 185 centimeters, so he's trying to get it up to like, you know, here. Right? How much force does he need to get it that high? So in terms of formulas, I would say, first question, is the direction that he's pulling the same way that the thing is going to move? Yeah, I think so, right? Because he's pulling up, and the barbell is also going to go up. So that does count. So it's not a trick question like that. So work is equal to force times distance. We have that work number. It was 6,000.0. And you know how it's supposed to be joules? Could I just go right to Newton meters? Would that make sense just to go right to that unit instead, rather than write J for joules? Now, I don't know what the force we used was, but I do know that my distance was 180 centimeters. Good. Now I almost caught the thing I'm going for here. Don't write this down. But if you were to try to do this, divide by 180 centimeters, divide by 180 centimeters, this meters and this centimeters do not cancel. Does that make sense? This is one of the reasons why we had to spend one of our first days of physics talking about how to convert unit types, because these unit types do not fit. So don't write what I wrote there. Don't even write the 180. Before we even write down that distance, we have to take 180 centimeters. I have to put it into meters. So what is centi? What's the little like 10 to the power of thing for centi? To the -2. Is that correct? So I believe 180 centimeters is 180 times 10 to the -2 meters. Or another way of looking at this, 10 to the -2 really means you got to move the decimal place back twice. So this is a 1.80 meters. Because I'm moving the decimal place over 2 times. Just put a little arrow there. Does that make sense?
Sure.
Okay, so first problem, do you get how the centimeters right here is a problem? Like we can't use centimeters, we need to be in regular meters.
I don't get one.
Okay, if I just put centimeters down here on the bottom, this meter right here, and this centimeter right here, they don't cancel. So I need to not use centimeters, I have to use just regular old-fashioned meters. So that's the first problem. So to do that, I've got to convert this centimeters into meters. Hopefully you recall centi, if you have one of those little charts. Centi is like times 10 to the -2. Or another way of looking at it, it means you got to divide by 100. So if you divide by 100, rather than it being 180, if you pull back 2 decimal places, it's 1.80. Now we should divide by that number, 1.80. Hopefully what you can see here then, you know how before I had centimeters on the bottom? Now that I have meters on the bottom, this meter right here and that meter right there, they cancel. What unit did not cancel? Newtons, yeah, N, capital N for newtons. Which is good, because that's what a force is, right? Forces are measured in newtons. So take 6,000 and divide by 1.80. And I got 3333 repeating. Okay, so we can't leave it like that, though, right? So there's a couple of ways we could fix this. One is we could use scientific notation and, like, move the decimal place over a few times. That'll work. 3.33, though, because we need 3 digits. Times 10 to the 3 newtons. Because you got to move it over 3 times. But then this guy has 5 digits. This one has 3 digits. So by the time you're done, you still need 3 digits. So that has 3 digits. There is another valid way of doing it. You could say 3.33 kilo newtons. I don't know that you probably would choose to do that method, but you know how like a 10 to the 3 is the kilo prefix? You can make it a kilonewton, kind of like a kilometer or a kilogram. It's now a kilonewton. That's all. So either of these two would be the right way of answering it. Depends on which one. If that works. This is my last one. Okay, good. Last one. Okay, so here we've got a crane using a bunch of energy to move a container. We want to find out how far the container was moved. So again, we're just using that same formula we've been using all day. One thing here, though, you see how it says that we use this much energy? Technically, then this 6.02, whoop, no, that's like Avogadro's number. 6.0 times 10 to the 2 is actually energy, capital E for energy. But isn't energy the same thing as work anyways? Does that make sense? So if that's energy, it's also equal to work. So work equals force times distance. We have energy, which is work. So this number is 6.0 times 10 to the 2. I'm going to use Newton meters again, rather than joules. The force is 260 newtons, and we don't know distance. So divide by 260. And hopefully what you'll see in this example is that the n can cancel, leaving you with meters. I go too fast? Okay, let me go back again. Let's actually do it with more room here. So work equals force times distance. We didn't have work, but we had energy, and that's kind of the same thing. So this number is 6.0 times 10 to the 2. Rather than saying joules, though, I'm going to use Newton meters, because I think that just helps visualize the units better. F is force, and we have that as well. We were told it was 260 newtons. The one thing we did not know was the distance it traveled, d. So how to get this d by itself? Well, it's being times by 260, so to get rid of the 260, you should divide. Does that make sense? He's not even watching. Okay. Well, you were the one who said that you didn't get it. Does this make sense?
Yeah.
Okay. If it doesn't, I can try it again. So.
I was just confused there.
So hopefully what you can see then is this Newton and this Newton here cancels. Does that make sense though why I really want you to write out your units? It helps. I know it may be, like for some of you may be like, I got this. Chris, I can handle this. But I promise you, as we get into more complicated formulas, if you've developed a good habit of writing in units, when we get to even harder formulas, it's a good habit to have. So. Okay, so 6 times 10 to the power of 2 divided by 260. I got 2.307. So 2.3 meters. Anybody else get that? Yep. Awesome. Okay. Quick summary, and then I'll let you guys work on. Well, actually, I have some suggestions, but let me do my summary first. We're at the point now where, for the next long while in physics, especially if you take Physics 20, most of what my lessons look like are I introduce a new concept, some definitions, and basically it's just there's a bunch of new formulas. And I'm going to say this a lot. If you understand math, you'll do good, right? So long as you understand the idea of how to add to both sides, divide to both sides. Eventually our formulas get a little more complicated. There is one that's coming up in the future. It says EK equals 1/2 mv squared. We're actually going to have to do some square rooting once in a while to get the v by itself. So hopefully that's something you're kind of familiar with, is square rooting both sides of an equation. But on that formula sheet, those are the only ones we're going to use this year. I did show you guys the formula sheet for next year at some point though, right? Where there's like 80 formulas on there.
80?
How many were on that sheet? There were lots, right?
Like 61.
I don't know. Well, should I find that sheet again?
There's a few more than the ones that are on this year.
There's a lot more, yeah. Like, here, let me find you my physics stuff. I'll show you. So here's the formula sheet that I give my physics 20 and 30 kids. And hopefully you guys would agree. Like, there's a lot of formulas on there. But honestly, it's very similar going forward. If you understand how to use a formula, you'll be good. I mean, it's not the only part. The other hard part is, can you interpret a problem? Because that's also a challenge as well. Because how many of you, when I did that one example where there was a force going one way and a distance going the other way, how many of you would have just times the two numbers together and said, that's the answer? You know what I mean? So part of it is you have to be able to interpret the scenario and say, wait. One of the forces is going this way, but the distance was going up, so actually this doesn't count. There is no work being done. So, okay, suggestions then. I know there's only like 10 minutes left. Don't waste the 10 minutes though. Like, do something to just kind of get a little further ahead. The two things I would suggest would be the assignment. More important though, print off the lab and start looking at the post-lab questions. Because sometimes you can answer some of the post-lab questions before you even do the lab. Last thought, and then I'll finally shut up for the day, because boy, I've talked a lot. Tomorrow, don't meet here. Meet down the long Holleteria hallway, and we're just going to go right there to start our lab.
So
Does that work?
Just bring the lab paper.
Just bring whatever stuff you bring to class. Just bring it to the long hallway there. And for about the first half hour or so, we're gonna race Hot Wheel cars down the hallway.
Yeah.
So, there is a lockdown sometime tomorrow apparently. I've been told this like I was told it was supposed to be like last week Tuesday and then Thursday and then it was supposed to be yesterday. So I mean, I've been told it's supposed to be tomorrow. So like if it happens during our lab, we're gonna have to go into like say either the gym or like the office or something, depending on how it goes. So yeah, we'll see how that goes. Hopefully the lockdown is not during our class. Okay, I'm done. Find something to do for the last 10 minutes.